So what we'll be covering today is distribution and transmission systems. So for the electrical power system, so as we generate power, as we saw last time, you can have wind, thermal, nuclear, diesel, all those kinds of things. It starts with the power generation itself. So now what you're seeing here is a simplified diagram from start to finish of the stages through which power passes in the main, what we call the electrical power grid. It is not a straight line, as you can see here. This is a simplified version for purposes of us understanding the various stages through which power goes, and specifically to understand what voltages we need to produce power at and to transmit power at. Now, what you will also realize is that we do transmit power at various voltages at different levels, and there will be reasons for that, which I will explain shortly. But first, let's go through each of the different stages of power generation. So the first stage is this section here. So up to that point, this is called power generation. So this is the generation stage, which we dealt with last time, and we talked of power being generated using synchronous generators or alternators that produce power at a certain voltage. Now, in most cases, for commercial use, you will have power generated at 11 kilovolts. That's 11,000 volts. Now, straight away at the generating station, you will have a transformer, which is symbolized by this. This is the symbol for the transformer. On the primary side, on one side here, you have power being generated by the generating station at 11 kV, and it is what we call stepped up to either 132 kV or 220 kV or 320 kV. After generation, the next stage we go to is transmission. So transmission starts from the secondary stage of the transformer all the way down to this level here, right? Now, so at this, within this, you have your 132 kV or your 220 kV or your 320 kV lines. So this is primary transmission, is where you do bulk transmission of power, hundreds of megawatts of power transmitted across the country from the power generating stations. So like in Kenya, you have certain areas where you have concentrations of power being generated. At the coast, we have a lot of thermal power. Within central Kenya, you have a lot of hydroelectric. Around Naivasha, Olkaria, you have quite a bit of geothermal. So these clusters of power generating stations produce a lot of power, more than what can be used at those areas, and they are transmitted nearer to the areas where they are likely to be consumed. So these can be areas of large population like Nairobi, Mombasa area, Western Kenya, places like that. Now, primary transmission, as we've said, is bulk power that is being transmitted. At certain points nearer to the load centers, you will have receiving stations. So the receiving station is near a large load center. So there is a step down transformer that now brings it back down from 132 kV or 220 on this side to 11 kV or 33 kV or even 66 kV. So what you will now find is whereby at the primary transmission, you are kind of consolidating various power generating stations, and it now distributes it near to the load centers around the country. So you'll have your load center, your receiving station, and then it sends out various lines, taking it closer to where it needs to be used. So at this stage, you can be at 11 kV, 33 kV, or 66 kV. Once you now reach to the load centers themselves, you now have what you call substations. So substations are local facilities whereby you have the power at whatever value it was received, either 33 or 11 or whatever it is, and being now further stepped down to a more manageable line. So now here you have what we call feeders. So a feeder is a line that will now take power to the consumers themselves. So once we have reached this level, we are now at distribution. So at this level, we are distributing to the consumers, all right? And then, of course, the consumers will be taking it either at 3-phase or at single phase. So these lines will be 415/240. This is called the one-line diagram of a power system. And these are things you can practically see as you walk around the country, as you move around the country, you will physically see these things. So from the one-line diagram, we now have the basic structure of the electric system. So you have your generating stations, generating at 11 kV. You have your transmission at 132, 220, or 320. Now you have certain customers, very large-scale customers, who can take power at that high voltage. Then from the transmission side, you then have the substation with its step-down transformer, and you have your power distribution network. So these are the various feeders that we were talking about. Quite a lot of manufacturing industries do take power at 11 kV because from the point of view of the power distribution company, it is cheaper for Kenya Power to actually supply at a higher voltage. Then finally, you have your customers who are at the secondary distribution level, the final level, which is 240 or 415. So at this stage, let's look at the Kenyan national grid. Now, this, of course, is not geographically accurate. The distances are not accurate, but it gives us a sense of the national grid at a transmission level, okay? So it shows you the major power generation areas and the major power consumption areas. The red lines are lines of transmission that transmit at 220 kV. These would be among the largest structures that you would see, the huge pylons that you would see around the country. So areas like this, Masinga, Kamburu, Gitaru, Kiambere, you can see this is a power generation center, okay? This is mainly hydro, right? Hydroelectric power, and you can see the huge amounts of power that these power generating stations produce. As you come down, you can see now these familiar names. This is, of course, Nairobi area, and Nairobi area is the largest load center in Kenya. Within Nairobi load center, you will notice that you have some small amount of power being generated from there. Iber Africa, which is 56 megawatts, is being generated in industrial area. And you can see now these stations that are being indicated here, these are actually receiving stations. So you had at the power generation sites, you have the generators, which are these. Then you have them being connected to through transformers. That line represents the transformer, and a line that links several of them together like this is called a bus. A bus is a series of points which have the same voltage and other characteristics, same voltage, same frequency. This is different from a transmission line, because a transmission line or a distribution line or any power line will tend to have voltage drop along it. But a bus is usually a short connecting line within the power station, within the receiving station, that connects points that have the same voltage. So the same thing can be seen from here, where you have places like Embakasi, Ruaraka, Juja. These ones, as you move around Nairobi, Dandora, places like that, those are the main receiving stations that receive the bulk power from the various power generation areas and step it down and circulate it around Nairobi. And you will notice that within Nairobi, the sub-transmission is at 66 kV. So actually, it's not very visible from here, but what you will realize is there is a ring that connects all these centers, all these stations together, and it is a ring of 66 kilovolt lines, so that all of those, the power can freely circulate around that ring. And then you have smaller substations inside the area, which have not been indicated in the map. Moving further around the country, some other places of interest. Another power generation area is this Olkaria. This, of course, is thermal. And an interesting combined area is this one here. So this is the coast. So the coast is interesting in that it has both power generation as well as a power consumption. So you have places like Kipevu in Mombasa, which generate power. Rabai is a big station, but it also has a bit of power generation. Then you have the consumption with the Bamburi and Kilifi, which are substations or receiving station. Another load center is kind of Western Kenya, so that is shown all around here, these areas. So Western Kenya is generally a load center, but it does have a few power generation stations like Sondu Miriu, which produces 60 megawatts. You will notice Tororo, which is in Uganda, which means that a national power grid can actually be connected to a neighboring country's national power grid. So in the case of Kenya, we are connected to Uganda, Ethiopia, and I think Tanzania. And Uganda and Ethiopia do actually sometimes supply us with power. So Uganda used to have surplus hydroelectric power. Ethiopia has huge hydroelectric power, which they have recently in the past few years constructed. So you can see the concept of a national grid allows us to take power from areas where it is really being produced to areas where it is being produced. One of the interesting things is electrical power, unless you have batteries, must be consumed as it is produced. So if power is being produced in Masinga, if Masinga, the hydros there are running, that power must find its way somewhere and be consumed instantaneously. So if you're producing 40 megawatts at Masinga, there must be a load somewhere that consumes 40 megawatts. You must be able to consume. So that means that it is a constant adjustment of the load centers and a balancing of the load centers with the power generation centers. I've shown you the transmission system, which is the power grid. The distribution system now has a bit of intricacy, which we can go into. So some of the key things you can see in this one, for example, here, this big device in the middle, this is a transformer. So every substation will have at least one transformer stepping down from the high voltage, which would be the incomers over here. And then you have various outgoing lines. In the distribution system, usually you will have what we call a radial system. So a radial system means that you have the substation, and then you have various, as we had said, feeders coming out of the substation itself, and these go and feed all the consumers, and those are indicated like that. So if we look into the schematic layout of a substation, it will look something like this. So on this end, we start with high voltage transmission lines. So the high voltage transmission lines will come into a substation. Now, in a lot of these setups, you will see quite a number of redundancies and protection systems. Protection systems are there to protect both the power system itself and human beings. If you look at this substation, you can see the whole place is very isolated. You can see there's gravel there, there's a wall there that prevents people from accessing. The engineers have helmets and protective gear. There is restricted access, and there is a certain way in which these types of facilities are constructed. So protection systems are put in place so that they protect both the system itself and they also prevent loss of life. So the protection systems that we have are, one of them is the circuit breaker. So you have, when the transmission lines first enter the system, you have circuit breakers, which are high voltage. In the event of a fault, the purpose of a circuit breaker is to literally break the circuit. It prevents these high voltage now from further coming into this section that we have. Okay, so if there's a fault within the substation, the circuit breakers will disconnect any supply, any voltage that is coming in, so that the fault can be taken care of. Next, we have what we had talked of, buses. So this 220 kV, the high voltage that is coming in, first passes through the circuit breakers and then is supplied to the buses. It reaches the buses. In the case of our diagram here, buses are these lines that are coming in, call them tubes, that run in between the various lines. But what that means is they are essentially conductors. Conductors do not have to be wires. Conductors can even be tubes or poles or wire. From there now you have the actual transformer, which is here. You can have more than one, so that you have two different lines being created or two different sections being created. These two rings are the symbol for a transformer, but they can easily also be represented by that symbol. In between here, this is your high voltage side and this is your low voltage side. Whether it is 220 to 11 kV or whether it is 11 kV to 415, there's always a high voltage and a low voltage. In the case of the substations in distribution systems, these are step-down transformers. So the high voltage will be the input, in this case 220, and the low voltage will be your output, in this case 11 kV. So once you've stepped the voltage down, you now have 11 kV. Once again, you have circuit breakers. We have protection at every possible point. Now another bus, which is an 11 kV bus. So the transformers each feed their own bus, from which you now have various feeders. In this particular case, you have what we are calling the bus tie breaker. If you would want, for various reasons, you may decide to isolate the two buses from each other. You can have a substation which has 2 or 3 systems that are isolated from each other. Once again, this is a form of redundancy, whereby in case there's a problem, say with this transformer, you can cut off this transformer at these 2 points, you disconnect the circuit breakers, and you have your feeders not being supplied. But on the other hand, you can decide to reroute, because that transformer is not working, you reroute your power through this, so that your bus tie breaker, when it is connected, it will allow power to flow from this transformer through and still supply your feeders. So we like to have various redundancies within electrical power systems so that you can ensure continuous supply of power.